Okay, so the next talk is going to be given by Han Su, who's titled Network Change Validation with Relational NetKAT.
Oh, yeah, you are right.
Go ahead.
Okay, so let's get started. Today I'm going to talk about network change validation with Relational NetKAT. I'm Han. This is a joint work with Dave, Ratul, and Zach. To begin with, I would like to say networks are large, therefore it is very hard to maintain them. Network companies like Microsoft, Google's, or Rogers all suffers from network misconfiguration, which has brought them millions of loss to themselves and to the society. Therefore, it is important to develop some kind of automated tool for us to debug the network. And that kind of tool is called network verification. Most network verification in the context can fall into this kind of category. Given a static snapshot of network N, such as the network here, I show 4 devices like device A, B, C, D, and thousands of other devices which is not shown in the picture. I also show some of the link between these devices. So given a network like this, we want to make sure it is safe. We want to ensure properties such as reachability, whether a packet sending from device A can finally reach device D, or we care about loop freedom, such as packets sending from device A will never reach A again. During past 2 years or so, network change verification has achieved great success. However, this notion of network verification doesn't fit into the development of network. And let's see through an example. Suppose you are a network engineer and you are taking in charge of the network here. One day, you find all the link towards device D becomes unstable, so you like to take device D down for inspection and for maintenance. During the time for maintenance, you would like to make sure that the network still functions correctly. So you decided to make an update. That is, you decided to reroute all of the traffic through device D now through device B. And everything you want to make sure is that you have to make the update correctly. However, this kind of change is really hard to capture in the traditional network verification. In traditional network verification, we will give a set of property P for the pre-network. This network contains thousands of devices, so that the property P is a very coarse and approximation towards the network. Such as, if we care about the reachability property, it will contain millions of reachability pairs. Instead of stating this reachability pair one by one, we only state the reachability between some of the devices we are interested in. And then we go to the new network. We will state another set of property P prime, which may or may not be the same with the property P. But this property P prime is again too coarse to capture the change you have made, such as the reachability between some very far away device will never be able to capture the internal rerouting you have made. And you definitely don't want to state the change by looking through this network with thousands of devices and millions of reachability pairs. So the question is to ask, can we focus on the change itself instead of doing so on the whole new network? So this notion of network verification is called relational network verification. In relational network verification, the problem is stated as follows. Given us pre-network N old and a new network N new, is new network updated exactly from the old network under the change specification S. And our job as a programming language researcher is to develop a language to describe network changes. Of course, we are not the first one to do so. There's one prior work called RELA, which focuses on one particular network change called path change. Originally, you are forwarding data through the device A, B, C, and now you are going it through A, D, C. In our work, we would like to demonstrate relational NetKAT, which focuses on generalized notion of change, which is trace change. The trace is sequence of packet, PK0, PK1, PK2, representing how packet is modified and transmitted inside the network. So what are traces changes, and what is relational NetKAT? Let's move on to our next section, the language design of relational NetKAT. The first concept I would like to introduce you to is the idea of traces. Here is an example network with 7 devices, A, B, C, D, X, Y, Z. And I here show 2 of the example traces, the right trace above and the blue trace below. The right trace above shows how we forward the packet from device A, finally reaches device Z, and it contains 4 packets. Each packet contains important header information like source IP, des IP, protocol type, as well as the location information, such as the packet 1 here denoted has a location field B denoted that it is now transmitted to the device B. In certain point of view, or in the language of NetKAT, we view the network as set of all possible traces, such as this network will be represented as a set of red trace and blue trace. This idea of viewing network as set of traces, suggesting we are treating the network as a system of how to transmit and modify packets from devices to devices. Now we have the idea of traces. Next, we can come to our problem. We are going to make the rerouting from the device B and device C. How are we going to do this? How are we going to describe this? So next, we are going to formalize it and formalize the network changes. So let's restate the problem. Originally, we got a network written in the NetKAT denoted by KO, which contained two traces, which is the red trace and the blue trace. Now we are going to make the rerouting from AVDZ to the ACDZ. So here we change the red trace to the green trace. Now we got a new network, which is a new set of traces contains the green trace and the blue trace. So the problem now is how are we going to describe network changes? A simple idea is to describe network changes as trace relation, which is the set of trace pair. In this case, we'll describe this change relation as a red to green trace pair and blue to blue trace pair, suggesting that a red trace in the pre-network corresponds to a green trace in the post-network, while the blue trace remain unchanged from the pre-network to the post-network. Using the triangle as a notation of applying a trace relation onto a trace set, our verification goal can be stated as K_old under the trace relation R change is equivalent to K new. So now we have the idea of network and network changes. The next step is to introduce the design of relational NetKAT, which is what are the anatomics for describing this R change relation. So this network change contains two trace pair, which is red to green, blue to blue. Let's first focus on the red to green trace, which is a trace pair of PK0, PK1, PK2, PK3 to the rerouting of itself. So first thing first, let's first view at the things happen at device A, which is before we enter in device B, nothing has changed at all. Therefore, the first anatomic we need to describe this kind of trace relation is a relation suggesting nothing has changed at all. And we would like to use the construct of ID or traces, suggesting that all of the traces should be mapped to itself. Nothing has changed from the pre-network to the post-network. How to describe it? We will use the language NetKAT. In NetKAT, a NetKAT expression is interpreted as a set of traces, and the set of all traces can be expressed using the language NetKAT. Therefore, the first construct for our language relational NetKAT is ID K, suggesting that all of the traces belongs to the NetKAT expression K should be mapped to itself. And then let's move on. Since we have dealt with the things happen at device A, the next step is to do the things at device B and device C, where we have a rerouting from where we reassign the location field B to location field C of the packet 1. Therefore, we introduce two new constructs, which is delete sec, insert sec. Delete sec location assigned B, followed by insertion sec location assigned C, suggesting we are doing a reassignment of the location field from B to C. Combined with the things we talked on previous slides, we can now describe the things happens at device A, B, C, which is ID or traces, delete sec, and insert sec. Putting things together, now we can describe, now we can have three new language constructs, which is delete sec, insert sec, and the regular concatenation R1 with R2. Finally, let's finish the discussion about the red to green trace relation. Now we have dealt with the things happens at device B and device C. And next, we move to device D. Since nothing has changed at all after the rerouting, the packet 2, packet 3 should remain unchanged in the post network. Therefore, we again assigned an ID or traces at the end of our language specification. So here, the R reroute suggests all of the traces that has gone through a rerouting. Similarly, we can describe the things that has not be changed from the old network to the new network, which is the I preserve. We use the language ID or traces, location doesn't equal B. All traces, location doesn't equal B, is a NetKAT expression suggesting all of the traces doesn't go through device B. Using ID, we are suggesting that all of the things doesn't go through device B should remain unchanged from the old network to the new network. Combining all these things together, we can finally state our specification for verifying the rerouting happens in this network. That is, the K-old triangle R reroute plus R preserved is equivalent to K new, suggesting all of the things in the new network is the things that have been rerouted and preserved from the old network. So this is the design of our language relational NetKAT. We reorganize and decompose the language construct we talked on previous slides into 4 basic but essential atomic, which are filter, map, insert, and delete. Besides, we also add the regular union, regular concatenation, and the regular star to compose this atomic into larger language specification. So here are all the things about the language. So the next step is how are we going to check this specification? What is the algorithm for this kind of compilation? As one familiar with automatic theory might notice that relational NetKAT is actually the NetKAT transducer. So the question is to ask whether we can apply the regular transducer algorithm onto our relational NetKAT. And the answer is, in most of the steps, it is true, but with one exception. Here is the whole compilation pipeline for checking K-old under the relation R change is equivalent to K new. Everything flows smoothly when we apply the regular transducer algorithm, but with one exception, which is the projection. It will induce a blow-up of at least the packet space size. It is really large because a 32-bit packet will lead to a 2 to the 32 blow-up here. So what's happening here? Let's first see the projection step on the regular transducer and the regular automaton. So here is how our automaton accepts a word. It will start with a state S0, and each time it takes an input alphabet, and then it goes to the next state, S1, S2, and finally to the Sn. And in our projection step, we first get an input of a regular transducer, which is length preserving. And this length preserving regular transducer will accept a pair of letters on each step, which is A1, B1, then it goes to state S1, S2, and finally to the state Sn. What does the projection step here do? It converts the regular transducer into the regular automaton by projecting the input alphabet of transducer onto its second opponent. That is, we are going to eliminate all of the letter A inside the transducer, so that every rung of the regular transducer will correspond to a rung inside the regular automaton. But things are slightly different in NetKAT automaton. And here is a rung of a NetKAT automaton, and you can see the difference here. Here, each state is paired with a packet, which we call a configuration. So what does this kind of configuration do? It actually faithfully represents how a packet is handled in the network. In the network, each device takes a packet as an input, then modify it and forward it as the output. So inside the NetKAT automaton, each time it takes the last input package, which is the packet 1 prime, and then modify it and forward it as the packet 2 prime. Promote this idea of configuration to the NetKAT transducer, we got a configuration of a packet pair, representing a packet relation from a packet in the pre-network to a packet to the post-network. Then the things goes wrong. That is, when we're going to do the projection, we not only need to project over the transition alphabet, but also over the configuration. There is no simple way to do so, and the regular transducer algorithm will make the PK1 explicit, which will directly induce a blow-up of at least 2 to the 32. So how to solve this problem? Let's get back to our first principle. Why are we going to design this language? Because changes are small. What does it mean by changes are small? And let's see through the NetKAT transducer. Here is a rung of NetKAT transducer, start with S0, PK0, PK0 prime, to Sn, PKN, PKN prime. And it actually faithfully represents a trace translation from PK0, PK1, PKN to the PK0 prime, PK1 prime to PKN prime. The changes are small here suggests that the trace translation from the trace in the pre-network shouldn't be too different from the trace in the post-network, which suggests that the packet at the corresponding position should be not too different from each other. That is, PKI should be very similar with the PKI prime. And this gave an idea of the key technique of our projection algorithm. That is, we should split the configuration by how much we change the network instead of the whole packet space. We'll classify the configuration by the PKI prime pair instead of the whole packet space. We were very happy to tell you the actual technical meaning of this sentence after you finish reading the paper, but for now, let's move on to our next section. Okay, since we have made an empirical or kind of philosophical observation as our key techniques, so the question is to ask, does it apply to the reality? So we performed an evaluation. We implement our language in the OCaml, and we combine our technique with all of the data structure optimization techniques that use in previous work. We use BDD, anti-mirror derivative, and by simulation-based equivalence checking. And we also implement an interface for Batfish and Ratul so that we can take the raw data input of these two tools and then verify it and give you the output. The first benchmark I would like to show you is a benchmark comparing with Batfish, which is a benchmark which currently no relational network verification tool can re-implement. So Batfish is a network verification tool in terms of the traditional network verification. Inside of its tutorial, it provides you with an industrial benchmark with over 200,000 lines of routing table information written in JSON. And during that tutorial, it guides you through step of changing the network, then verifying it. And in our work, we try to reproduce that procedure in our language as much as possible and give 5 test cases and their time. As you can see, all of the test case falls down below 30 seconds, which is perfectly suitable for our goal of iterating network by updates. The other benchmark I want to show you is the benchmark comparing with Ratul. So Ratul is a relational network verification tool where they use the Alibaba internal network, which contains more than 2,000 of devices and 20,000 of traffic classes. And we compare our tool on their data set. We randomly select 2,000 traffic classes out of 20,000 of traffic classes on 3 of the most commonly used Ratul specification and reinterpreted in our language. And these 3 specifications are preserved. That means you didn't change the network at all. The node deletion suggests you remove a device from the network, and the forwarding path change suggests you reroute a device to another. And the average of our work and the Ratul all falls down within 1 second. So it is suitable for us to iterate the network by updates using this kind of verification tool. And the other thing I want to mention you is that our algorithm or our observation actually applies. That is, our algorithms falls down 1 second, but using the traditional naive transducer algorithm, it will directly time out over all benchmark on all the test cases. So to conclude, the key takeaway I want to give you is networks are big, but changes are small. Therefore, when doing network development, we should describe and verify the network changes instead of doing so on the whole new network. And if better, use our language, Relational NetKAT, for it is designed for this. And thank you for your attention.
Questions? Yes.
Thank you for the very interesting talk. So I was wondering, you showed the performance, and you showed that you said that the philosophy is you described the changes aligned, basically, right? PKI, PK prime I. But what if you have a change in the network that maybe extends your trace by 1, right? So then you would have okay. How would it perform, and could you adapt your technique?
Yeah. Thank you for your question. This actually is some point we omit in our talk. That is, we directly goes to the projection step here. But before the projection, there is a step called cross product and epsilon elimination, which will turns the transducer, which may maps the words of different lengths into a transducer that is length preserving. Yeah, so there's a pre-processing before this projection step, so that we only need to care about the length preserving mapping in the case. So we can also treat we can also deal with the non-length preserving trace translation using kind of delete and insert. These two are non-length preserving.
I don't know. Maybe that's what you're saying, and I'm not, but on the next slide?
Sure.
Or the slide where you say our philosophy. Yeah, exactly, this one, right? And if you go to the next transition, here, right, so when you have two different, just so that answer, when you have two different traces from two different networks, where in one network, after the change, you actually have to do one or two more hops. Like, how is this compatible to this splitting of the configuration?
Sorry? Can you repeat the question?
If you have two traces and one has, but maybe we can take it offline. Actually.
Okay, sure, no problem.
Any other questions? Actually, we do have some time to elaborate on this.
Yeah, hello. So just to understand something, I mean, you are reasoning all the time about traces. So, but modifying a graph could imply that you have to reason about an exponential number of, I mean, I can modify one node, and this will generate, the modification of an exponential number of traces. I'm just wondering, whether it's a practical way, let's say, or a powerful way to reason only about traces when you talk about changes in graphs. So, you see what I mean, or? So, for instance, admit you have like a central node.
Yes.
And all the paths go through that one. See, and
yes.
Now you want to modify that one, change it with that, and some number of nodes and so on, and direct some whatever edges around and all these things.
Yes.
See, I mean, here there is a lot, this will touch a lot of traces. All the traces of your system will be touched by this little modification.
Yeah.
So I'm just wondering whether
okay.
you could have this situation. So because you see, I mean, in your slide that we see here, you say changes are small.
Yes.
Maybe local, what you mean,
yes.
at a trace.
Yes.
But the number of traces that you have to deal with and how to describe these changes is complicated in general, right?
Yes.
So is this an issue of your approach or no?
Thank you for your question. I think there are two aspects for this question. The first is the traces are not as large as 2 to the 32 as we, in our work or in the previous work, we treat them symbolically. It is actually very small compared to the 2 to the 32, though it is still very large compared to the constant number. And the second question is, can our work deal with large change? The answer is yes, but kind of the starting point of our work is to treat kind of this kind of small change. If you can make small changes and you can make large changes. You can just destruct all of the infrastructure in the old network and build a new one from scratch, and you can call that also a change. We can also describe this, but in this case, you should use traditional network verification tool because you can make little use of the knowledge you had on the pre-network towards the post-network. And but in terms of the networks are usually very large so that nobody knows actually what is going on globally. So every time the network engineer makes an update, they only make a small update so that they want to make sure the things doesn't go out of their control. And our tool is designed for them so that they can verify each time they update the network.
Maybe to ask the previous question in another way, have you analyzed the complexity of these kinds of verification problems, and can you characterize kind of when relational NetKAT would be a win versus maybe some other approach without the tool?
We only performed our evaluation in terms of the seconds, but we didn't perform a serial-optical analysis because kind of the key techniques we rely on is kind of empirical or hard to quantify over. But in terms of the complexity of each step for algorithm, we believe it is aligned with kind of previous work catch paper, and I think it is currently the fastest version of checking this kind of network NetKAT equivalence.
Yeah, one idea that might be interesting, there's an old paper by Tim Griffin in the database community, and he looks at incremental view maintenance. So totally different problem, but the same kind of incremental optimization, and looks at how, as the size of the change grows, the benefits of incremental view maintenance, start to diminish, and there's a tipping point where
down.
it's just better to recompute. And I wonder if there's a similar characterization you could give for this kind of calculus.
Yeah, we believe it's true, but sorry, we didn't have that in our paper.
Okay, let's thank Han again and move on to the last talk.